Hello everyone, Dr. Zia Tahir here. This video tutorial is the third video of vibration analysis series, and it is about experimental model analysis in MATLAB. So here are the highlights of it. Model analysis of a cantilever beam using time domain and frequency domain. So here is a system, so a cantilever beam. So at the end of that, an accelerometer is attached, and then a shaker is used to produce force vibration in the beam. So first, I'm going to show you how to perform time domain analysis, and that is the data for which I'm going to perform time domain analysis and then frequency domain analysis. That is a frequency domain analysis and then fast Fourier transform. So this model testing or experimental model analysis is very common in vibration studies. So model testing is a form of vibration testing of an object whereby the natural model frequency. So natural frequency, model masses, model damping ratios, and mode shapes of object under test are determined. So in this video, I'm just going to show you that how to uh, find natural frequencies. So that is a typical setup. So a structure, and in this video is a cantilever beam, and then a force vibration is produced by a shaker. Okay, and then accelerometers are attached, and then the data which you'll get, that is after processing the signal, so that is a time domain data, and then Fourier transform is being applied to get data in frequency domain. So time domain and then frequency domain, and components which are used, they are shakers, electromagnetic shakers, or sometimes some physical shakers are also used, but they are really old, and nowadays these electro dynamic shakers are used, and then an accelerometer, and then a force transducer. So this is again a model analysis, experimental. That model is study of dynamic properties of system in frequency domain. Example would include measuring vibration of a car when it's attached by a shaker. So that is a shaker which is responsible to produce force vibration. So it has a force transducer, so which uh, apply force, a constant force with varying frequency. And here are the shakers. A shaker is a device in vibration testing to excite the structure. So shakers are responsible to apply constant force with constant amplitude. So like as constant amplitude force, and that is being applied sinusoidally. And shakers, they can produce constant frequency, and then they can produce varying frequency. So here is a typical example. Electrodynamic shaker system consists of a shaker and a matching linear direct coupled power amplifier. So they are very much in use, and here is a typical study. Like I am using here a cantilever beam, and the similar study can be performed like on a wind turbine blade. Is a prototype wind turbine blade, and here is a vibration shaker. So it will produce, it will give it excitation, and then there are accelerometer. They are attached at different ends, and they will give acceleration. In this example, in this example, force is applied. A constant force is applied in a frequency sweep. So frequency changes from like as 5 hertz to 300 hertz, and then response is being measured. So because the force is being applied, that is a constant response. So the displacement or acceleration must be constant. But in this case, there is one peak here, and this peak corresponds to first resonance Then there is another peak that corresponds to second resonance, and then there is a third peak which corresponds to third resonance. So in this analysis, so first three peaks are being computed. So the first is time domain analysis of signal to check resonance. And here in the MATLAB, I'll have, so that is the data, cantilever beam frequency from 5 to 30 hertz. And that is the data which is available. So it has time in second and displacement as millimeter. So if I try to plot that data in Excel, so here you can see, so there are three peaks in that data. So three resonance frequencies are associated here. So data usually from data acquisition system or sensor data that is in text file form or that is in CSV file or sometime in Excel form. So in MATLAB, you can use that built-in function import data file name, and then so this is function import data. You can use that to import data, but here I am going to use read table built-in function in MATLAB. So this read table function can read the data and then uh, save it is in as a table form. So it can take text file, data file, CSV file, Excel file, or even XML file. And here is the read table and file name. And then the option like if you have Excel data, so you if you want to import a specific sheet for that. So I am then here, I'm going to import data. So that cantilever beam file widget extension and read table. And here you can see that. So this one I'm going to apply. So it gave you a warning. So and here you'll get the data. Here it is a time and displacement. So I from the table, and then I am going to take those. So here I have time and displacement. So then plot amplitude of vibration, displacement or acceleration versus time. And so plot amplitude of vibration is usually displacement or acceleration, but in my case is the displacement versus time. And for that, I am going to use that 2D plot command. So plot X and Y, and then like you can read it further, how to give name or how to access title, and then legends, lines, lines, markers. So everything is there. So now I have here plot time and displacement, and R is right, line is red. So I am going to plot that data. So this one is the time domain representation of data. Domain representation here is on horizontal axis is time, and then is the displacement, and then MATLAB script for that. Here is the first is a plot one, so figure one. So that is a figure one, and here you can see that it shows you as a figure one. And then the grid down and the title is the time domain. Response of cantilever beam horizontal axis time uh, in second and displacement in millimeters. So this is the time domain representation. So in the time domain, I can clearly see. So that is actually so the displacement. This displacement is from it is between -1 and 1, and here it represents first peak. Here it represents second peak, and that is the third peak. So these three peaks represent three different natural frequencies. And then here, this data is recorded for frequency sweep. So initially frequency is 5 and the end is frequency 300. Here you can see that. So for the first 2 seconds, so that are the waves. So you can see that there is a space between each cycle, and here in the last one you can see, so they are very closely spaced. So here here at the start, the frequency is low, and in the end is frequency high. So now from here, from the time domain analysis, now I can see from the time domain analysis, I can see that so these three peaks represent three different natural frequencies. Next step is frequency domain analysis using fast Fourier transform. So FFT is a built-in function in MATLAB which convert time domain data into frequency domain. So that is a frequency domain. So I'm going to show you how to do that one. So in MATLAB, I am going to now, so FFT built-in function I'm going to use, and that is in syntax of that y is equal to FFT and then n for that, or sometime is a dimension. So YFFT compute discrete fast Fourier transform. Discrete Fourier transform DFT of x using fast Fourier transform algorithm, and that is syntax x and then dimension. So what is n here? So n is the that is transform length specified as a non-negative integer, and this n must be like n that must be greater than total length of the signal. And this is a command, like if you have signal, so it automatically this one 2 next power of 2, so it automatically give you the what value is required. Okay, so if n is equal to 0, then FFT returns an empty matrix. So first, so this n must be greater than length of signal, and n must be in 2 raised power something. So here is like how to apply it. So to apply it, sampling frequency is required. Fs is a sampling frequency, so you need to find that the sampling, what is the sampling frequency when the data is being recorded. So, and that is a signal, and here YFFT, and here n is not being given. So when you're going to use compute Fourier transform of the signal, and then it compute the two-sided spectrum, then compute the single-sided spectrum P1 based on P2 and the even valued signal L. So then first it will find P2 is a two-sided spectrum, and then it's taking half of it. So P2 is equal to P1 is equal to P2, 1 to total length half 2 by 1, and then it is going to convert that P1 into even valued signal length. So, and then once this you found out, the next one is required define frequency domain F. So frequency domain F is required in the plot single-sided spectrum P1. So basically, first you need to define frequency domain, and then you need to plot it P1. So here that F is equal to Fs, which is sampling frequency, and it is being normalized with 0 to L by 2 divided by L, because we are taking single side of the spectrum, so half of the length. So that is now, here you'll have, this is the uh, frequency domain analysis. So here on horizontal axis is frequency, and on vertical axis is P1F. So that is a spectrum. So P1F. So while using that fast Fourier transforms is not always so it's not give you here the amplitude of vibration. So it give you simple spectrum. So what now if I apply it, so then I need to get that type of graph. So now plot function, so frequency domain response, okay, of cantilever beam. So first I need to find L. L is the length of the signal. So that is the signal displacement. So I find out its length, and then I need to find sampling frequency. So sampling frequency, because in this case I have time as time up to a few seconds. So like, so I'll find out that Fs as what is the sampling frequency. Okay, so if I'm going to apply it, so it comes as 601. 601 because it takes at the first value as 0, or otherwise you can see that simply uh, fs find signal minus find when the time is equal to 1. So this one, this signal, what is trying to do is it is find approximate time. So when it is 1 second, and then it find its index. Okay, so using here, so now I'll get that length of the signal 1200 and then frequency of the signal as 600. So that is the simplest command. I'm using it, but I'm not much interested in that now. So the next one is need to define n. So n is equal to, n in this case I'm using, n is 2, next power of 2 as L. So what it does, it find what is the length L, and then it find 2 raised per n, so it is greater than that L value. So this one, so it says that n is 1634. Otherwise, you can choose your own value. Okay, so if you're using that higher value, like that is a minimum one, whatever is the n value. But if you are using a higher value of that, so then the solution starts converging. So you can, like, if it comes as 2 raised per 13, so you can go like 2 raised per 14, 15, up to a number when the solution will start going to converge. Then this is a command x FFT. So the function, sorry, here is the displacement, which I have already there. That is the displacement. So it first find transform of that function and then compute two-sided spectrum. So P2 is a two-sided spectrum and then compute single-sided spectrum from that. So that is a P1 is a spectrum and then define frequency domain. So that is F is equal to Fs into 0 to n over 2 over n. So that is the uh, frequency domain, and then I'm going to plot that figure 2. So plot F versus P1 for, and the blue color grid on, and then so that whole script I am going to run. So now what I'll get, so that is I'll get here. So there are few peaks and each peak correspond to resonance frequency. So in time domain analysis, so there were three peaks. Okay, but in frequency domain analysis, there are certain peaks, and these peaks which are at 50, 100, 150, 200, and 250, so they are not the exact peaks. So the peaks are somewhere here, correspond to 15.12.4, or then correspond to somewhere 81, and then there is some peak. So to get clear peaks on that, so I can adjust the value of 2 raised per n. So instead of 2 to the next power, I'll use that n is equal to 20 for that. Okay, so let's see what is the difference between them. So first I'll use, so here it is for 2 raised per 13, I think, I believe so. And then the next one, I'm going to comment that, and then like I can take any other value of n like 2 raised per 20, and for that one I'm getting the same one. So this is how you can find out natural frequencies. So this one sometimes several p correspond to the noise, but I can see like here in the time domain, so there are three peaks. So in the frequency domain, there must be three peaks, but like one peak as constant interval of 50, so that is possibly some noise. So then we need to get rid of these values. And like if you are going to adjust the value of if you are going to adjust the value of that 2 raised power, let's say if I do it 16, so with that one, so the peaks are slightly, their peaks are slightly adjusted, and then here you can see these peaks are appearing. So the next step is we need to find out that which peak correspond to the exact natural frequency. So once again, from the time domain, I can see there are three resonance, first, second, and third. So there must be three peaks. So this is frequency domain analysis, and the value here somewhere it is, which is 12, and somewhere value here it is like here the value is 81, and possibly somewhere here the value is 218. So now that frequency domain, so like I can say here noise as 50, 100, 150, 200, so that and 250, that is a noise. But again, to check that if it is a noise or not, so next we need to exactly identify these frequencies. So the next step is fast Fourier transform of segments of signal correspond to each peak to plot frequency domain. So next what I'm trying to do, I am trying to just take this segment out, correspond to the first one, and then correspond to the second one, and then correspond to the third one, and then I identify that. So what is the actual frequency correspond to the first peak? So what we need to do, divide signal into segments and then apply fast Fourier transform to each segment to find first natural frequency for each resonance. So from this figure, I can see that first resonance is between 0 to 2. So first I'm going to plot that data, and I'm taking that segment of data from 0 to 2. And I is the find index when the time is 0, and j is find index when time is 2. And then I need to get time from 0 to 2, and the displacement correspondingly 0 to 2. So and then I'm going to plot that figure 3. So figure 3 is now, so this one is time from 0 to 2. So like here you can see, so only the data which is from 0 to 2 is being plotted like this one. So now I am going to apply fast Fourier transform on this data only, like from 0 to 2. Okay, and again, now the data is now a displacement 1. And this is a frequency domain, so is a very much similar to the previous one which I have used. So I'll get that sampling frequency, and then I am going to plot that one. Okay, so now this is being plotted, and this one, when it's being compared with this signal. So when I have segmented the data like from 0 to 2, so now I can see in the figure 4, like that is the actual peak. I still have that 50, but not that all that peaks are now less significant, and only this peak is more significant. Okay, so in this way you can find out the data, or otherwise what you can do, like, so instead of going from 0 to 2, in the next stage you can see the clearly peaks are between 0 and 1. So between that, so then you can change the data from 0.4 to 1, and then you can run the analysis. Okay, so I'll see that what's going on now. So here, so that is the figure 3. So that is the data which I have just plotted like between so zero point 0.4 to 1, and then I'll have that figure 4 now. So that is a figure 4, and now that peak is much clear previous to the other one. So it means that although I have here, when I plot the whole data, so there was a peak, so that is just a noise, and now this one is the actual value. Okay, so then I can plot it between whatever is the value I want, like as from 0 to 25. So now I am putting X limit on it, and then I'm trying to find that maximum peak on correspond to that one. So here is like the figure 4, I'm going to plot it again, and then here you can see, and then the natural frequency is 12.89. So this is better accuracy of that. So 12.89 is the more accurate one. So that is now first resonance frequency. So now I'm trying to find the second exact frequency because there are few more peaks. So the next one is I am going to now. Now the next one is the other peak is between 4 to 6. Okay, so I'm just going to segment that data from 4 to 6 and then plot that. So here is in time domain, I have first take the data from 4 to 6 minutes, and then I am going to plot that one. So here is the data from 4 to 6. So here you can see that I have took the data from 4 to 6, which correspond to the second peak from here, and then I'm going to apply fast Fourier transform on that segment. And here is the same one, the script is the same. Okay, and I'm going to save that as figure 6. So here you are. So now again in this segment, so that is between 4 to 6. So now for data between 4 to 6 seconds, so now I can see that still the previous one 12.5 something, that peak is there, and that 50 peak is again coming. And now as compared to the previous one, this peak is more prominent. So to get further accuracy on that, I need to refine that uh, this time to domain data to a new one, like as I can see that the peak data is between 5 to 5.4. So now I can change that. Previously I used that 4 to 6. Previously I used 4 to 6, and now I'm going to change it to 5.0 to 5.4, and I'm going to run that analysis to plot that data in frequency domain, and then in, so here you are. So now that is the data from 5 to 5.4, and now you can see that there is a one peak correspond to 82.03. Okay, so now still there is one peak there. Still there is one peak there, and this is a true one. This frequency is a true one, like correspond to 81 point something. Okay, so that is now frequency for the second mode, which is 82.0312, and on that data I'll get that. So now for second resonance, I'm trying to put the limit between 50 and 100, and then I'll get the maximum value of here, maximum value of spectrum I am trying to find, and then corresponding frequency of that. So I'm going to replot that figure 6 here, and then the second natural frequency I'll find out. So next second natural frequency peak value at that comes as 83.013, and here you can see that. So it is somewhere 81 for that peak, and then so that is a second natural frequency, or that is the frequency correspond to the second mode. So in this way, we can find out accurately second natural frequency, but you can't do it directly. You have to first find out that where the peak is. Initially, I checked it, peak is between 4 to 6, and then I identified that which peak correspond, and then finally I got the value between 5.5 and 5.454. So in this way, so I have filtered that second peak. Another frequency correspond to the third peak, and it is somewhere between, I can see the peaks are really between somewhere 13 to 16 or 17 or onward. So this time I am trying to plot this data between 30 and 20, but I can clearly see that there is a one peak here, but there is a possibility of any peak here, or it is just a noise. So if I look back here, the data is basically when there is no resonance, it is between -1 to 1. So, and then this one is probably the same data. Okay, but I'm going to perform now the analysis between 13 to 20. Now that is a script for 13 to 19 time, like as from 13 to, let's say, 19, or I can go here like 20 or 19.5, and then I'm going to plot this one. So what I'll get. Now this figure 8 is very much similar to the previous one. So I need to limit that data correspond to peaks, so I'll clearly see that where the peaks are. So I can see here the peaks are between 13 and 16. So I'm going to change that data now 13 to 16, and then I'm going to plot both of these. So between 13 and 16, so now I can see that peak somewhere here is clearly visible. Okay, and rest of the peaks are not there. So still that peak is not visible. So again, I need to limit that data from, let's say, now that is a peak. So like somewhere between 14 and 15. So 14 and then between 15. So I'm going to plot that one. So now here is now, because that 50 peaks comes every time. So this peak is now is much clear previous to the previous figure, and then it corresponds somewhere between like 21, and it's not a peak, a single peak here. So now from here I can see that at 150, right at the start, which a peak was observed, so that is not the actual peak. Okay, so the actual peak is somewhere here around 218, but I can see that there is not a very clear peak. So to get that clear peak, further we need to further, because this one I got between 14 and 15, and now between 14 and 15, now again I need to, so I can see that here above 1.5, so there are some signals there, and then again here below 1.5 there are some signals. So I can now plot it between 14.3 and 14.7. So now instead of 14.3 and then 14.7, and I'm going to get that that both figures again. So now it is very much clear. This time between 14.3 and 14.7. So now I can see a clear peak at somewhere at 220. And still that 50 is not much relevant. Okay. So now that one is the actual peak. And to get rid of this, I can plot it between 220 and 250. And then between that, I'll find its natural frequency. So 200 and 250. Okay. And then I'll find out its corresponding natural frequency, W3, which is the third natural frequency. So that is the third natural frequency. So then, okay, so now I can see here. So that is the third natural frequency. Oh, sorry, that is for third mode. And the third natural frequency comes as 220.3125. And then here I have, so now because by doing that iterative process, now I can see that the third peak is between, actually it was 218 and now it comes as 220.312. So that is the third mode. So now based on the iteration, now I'll get that uh, whole of that script. So I will run it and then I'll find out that uh, what are the natural frequencies, omega 1, omega 2, all those natural frequencies. So now that is the time domain, frequency domain. And now I have plotted that figure 4. So that is between 0 to 50. So its frequency is 12.8905. Then the second frequency is 82.0312. And then here is the third natural frequency, so which is 220.312. So in the script, I have also got those omega n1 12 to 82, and the third omega n3 is 220. So in this way, I can this way, so a model analysis can be performed. So actually, model analysis is not about finding natural frequency. It is also about finding natural mode shapes, or then sometime in some cases that is to find model masses and sometimes the model damping ratio. Okay, so if you have to find the damping ratio, so it is simple, like from the first peak to that point. So you can find out like what is the logarithmic decrement between them. For the second one, it is again possible to find logarithmic decrement for that one. So if you want to watch some basic video about like what I have explained in this one, because this is the third video of that. So the first video here in my channel, you can find vibration analysis, time domain representation, and then second one is the vibration analysis, frequency domain representation using fast Fourier transform. So that is all about this video. Thank you very much for watching. So I hope you like this video. So please subscribe my channel for more videos on vibration analysis in MATLAB and then vibration analysis in SolidWorks, ANSYS, and Abacus.